Yeah, hello everyone, my name is Pei Rui, and today I'm going to talk about Van der Waals ferromagnetic material, iron germanium telluride. This is my outline today. I will go through some general features of this material and then show our measurements of its magnetic behavior and topological structures. So in the first figure, I'm going to show its structural diversity. As you can see, it is formed by a hexagonal lattice, and the side view diagram shows the most important feature of this material. That is, one of the iron atom, we can just call it Fe1 atom, can be located above the germanium or below the germanium. And furthermore, it may also form a vacancy structure. So there are three possible configurations. And in the figure 2, I'm going to talk about the magnetic response. It is the empty curve measured by squid. And first, we can see obviously that the material shows magnetic anisotropy. Also, there are multiple transition points which correspond to different underlying magnetic mechanisms. The most important part is that its Curie temperature is 310 kelvins. So it's a 2D ferromagnet at room temperature, which is really rare. And the empty curve clearly shows the hysteresis behavior. And as we can see, the coercivity is quite small, merely 25 OE. Also, at low temperatures, the coercivity starts to decrease. And now we finally move on to the SEM images. In the large-scale image, we can clearly see that there are two regions, and they're separated by a sharp border. And as we zoom in the boundary, we can see that in region 1, there are dark and bright patchy areas. And however, in region 2, there are numerous dark spots within a relatively flat background. And also, as we measure the monolayer height to be about 1 nanometers, we confirm that the two regions are in fact of the same layer. And now it's the atomic scale image. The SDM image in the center is measured from region 2, and it shows a lot of defect dark points, as you can see here. And the fast Fourier transform shows that it is exactly a hexagonal lattice. And also the lattice constant is 0.4 nanometer. We further analyzed the height line profile, and we concluded that the pristine side is of UUU configuration, and the defect side is precisely the Fe1 vacancy. Okay, in this last figure, I would like to talk about an interesting phenomenon. When we conduct our experiment at room temperature, we observed that the dark points were moving. And at first glance, it sounds weird because normally we think that the defects shouldn't be able to move. However, previous theoretical calculations says that the diffusion energy is for the Fe1 atom is comparable to room temperature. It's about 36 milli-electron volts. Therefore, it turns out that this observation of defect dynamics indeed confirms the theoretical calculation, and also it shows the instability of this special Fe1 atom. Okay, it's the end of my presentation. Thank you very much for listening. And if you have any problems, please do not hesitate to contact me. Thank you very much.